Write-through versus write-back. This is caching, and specifically the half of caching that almost nobody teaches, what your cache does when the data actually changes.
8:30 in the evening. A customer opens your app and fixes their delivery address. New street, new house number. They tap Save. The page says Saved, green tick. They close the app and go to bed. 40 seconds later, a routine deploy restarts that service. Nothing crashed. Nobody made a mistake. It was an ordinary restart, the kind you do every week. The next morning, the parcel goes to the old address. And here is the part that should worry you. Nothing in your log says anything went wrong. The database simply never heard about that change, and the customer has already seen you promise them it was saved.
So let's name the subject properly. This is caching, but not the part you have already seen. Almost every explanation of a cache teaches the read. You ask for something, the cache has it. You skip the database, everything is fast. That is not this video. This is the write path. What happens the moment the data changes and there are suddenly two places holding it? The area has a name, cache write strategies. 3 are worth knowing: write through, write back, which some people call write behind, and write around. This is not about why you cache at all, and not about where the copy lives, CDNs, edge servers, browsers. It is not about HTTP expiry headers either. Different tiers, different videos. This one is the write. Here is the idea that makes all of this make sense, and it is the bit people skip past. A cache is not a shortcut. A cache is a second copy, which means the instant somebody changes something, you have two places holding the same fact, and they are free to disagree. Your entire job on the write path is deciding which one becomes true first. Picture a waiter taking an order. He can write it on his pad and immediately punch it into the till before he walks away. One action, both places. The pad and the books can never disagree, but he stands at that till on every single order. Or he writes it on the pad, says got it, walks off, and punches the whole hour into the till later, all at once, much faster. But for that hour, the only record of your order is a piece of paper in his apron. Let's start with what is actually in most code bases, because usually it is none of the three. Here is an order store. Reading is cached. Look in the cache, and if it is not there, go to the database and put the value in the cache on the way back. That is called cache aside, or lazy loading, and it is perfectly fine. Now look at the write. It writes to the database and says nothing to the cache at all. So the database is correct, and the cache is still holding yesterday's address, serving it to every read until the key expires. This is the third option most people are running by accident. It was not a decision, it was an omission. Write-through fixes that in the most direct way there is. One operation writes both places. Look at the order because it matters. The database first, and only if that succeeded, the cache. If the database write races, we never touch the cache, so the cache can never end up holding something the database refused. And notice what is missing here. There is no invalidation logic, no expire to tune, no remember to delete the key. The cache is updated by the same function that changed the data, so it cannot drift out of sync. The two copies can never disagree. That is the whole promise of write-through, and it is a strong one. Now, the price. I measured this on a real database on this machine. A durable write, one that has genuinely been flushed to disk so it survives the power going out, took about 6 milliseconds. Writing that same value into an in-memory cache took about 1 microsecond. 6 milliseconds against 1 microsecond. The cache write is roughly 5,000 times cheaper. Next to the database, it is free. So write-through costs you those 6 milliseconds on the hot path of every single write, forever. One connection doing nothing but durable writes tops out somewhere around 170 a second. If your write rate is low, you will genuinely never feel this. If your write rate is high, it is a tax, and every writer pays it. Write back turns the order around. Write the cache. Tell the user yes. Get to the database later. The write path is 3 lines now, and it never touches the database. Put the value in the cache. Mark that key dirty, meaning changed but not saved yet, and return. Then a background worker wakes up on an interval, takes whatever is dirty, and writes it to the database in one batch. 2 things happen. Writes get dramatically faster because the user is no longer waiting on a disk, and the database stops seeing spikes. A burst at the front door arrives as a smooth trickle, because the flusher goes at its own pace no matter what the traffic does. That is a real win, and it is not free.
Here is the line I actually want you to take away, because this is the thing that gets described wrongly almost everywhere. Write back does not make the write faster, it makes the write a promise. Look at what really happened. You told the user, saved, and at that exact moment, the only copy of that fact is in memory on one machine. The database has never heard of it. The user has a green tick, and you have a piece of paper in an apron. For the whole window between the acknowledgement and the flush, that data is not saved, it is scheduled. And a process restart inside that window does not cost you performance. It loses data the user already watched you confirm. Those are two completely different kinds of bad.
Let's actually do it, because this is worth seeing rather than being told. Save the new address through the write-back path. It returns saved. That is what the customer sees on their screen. Now the process restarts. And I am not simulating a crash here. I am simulating a deploy. The cache lives in memory, so the memory goes. Now ask the database for that order. Nothing. Not a stale value, not the old address, no row at all. The write the customer watched succeed does not exist anywhere in your system. Here is the same sequence against write through for contrast. Save, restart, ask. It is there. That is the entire difference between the two strategies in 4 lines of output.
So why does anybody accept that? Because of this. Take a key that changes constantly, a shopping cart, a view counter, a live position. Say it changes 900 times inside one flush window. Write-through performs 900 durable database writes. Write-back performs 1, because the dirty map only keeps the latest value for each key. The other 899 never reached the disk at all. They were overwritten before anybody asked for them. I timed both. 900 writes committed one at a time, 5¼ seconds. The same 900 in a single batch, 13 milliseconds, just under 400 times faster. That is called coalescing, and for hotkeys, it is the whole argument. Which brings us to the number you have to decide on, and then say out loud. Write-back buys you throughput with a durability window. The window is how long a confirmed write can sit in memory before it is genuinely safe. If your flusher runs every 5 seconds, your window is 5 seconds. And that is your answer to the real question. How much confirmed data are we willing to lose? This is the part I want to insist on. That window is not a bug you fix. It is a number you choose. 5 seconds is perfectly reasonable for a view counter and completely unacceptable for a payment. The failure is not choosing 5 seconds. The failure is having a 5-second window and not knowing that you have one. So if you are going to run write-back, these two things are not optional. First, the queue has to be bounded. If the database gets slow and you keep accepting writes into an unbounded dirty map, memory grows until something kills the process, and being killed is precisely the event that loses the data. So above a limit, you stop being clever. You write straight through, synchronously, slower and correct. Second, the flush has to be monitored, and the metric is not, is the flusher running? It is how old the oldest unflushed write is. That number is your real durability window, live, right now. A silently stalled flush queue is not an outage. It is slow-motion data loss, and it looks completely healthy until the day you restart. There is a third strategy, and it is worth half a minute because it solves a different problem. Write around. Write straight to the database and do not put the value in the cache at all. The cache only picks it up if somebody actually reads it afterwards. Why would you want that? Because an enormous number of writes are never read. Log lines, audit rows, a nightly import of 2 million records. Write-through would push every one of those into the cache and evict the things people are actually asking for. Your hit rate collapses because of data nobody wanted. Write around keeps the cache for things that get read. The cost is honest. The first read after every write is a guaranteed miss. So here is the fair version of both, because neither one is simply the right answer. Write-through gives you 2 copies that can never disagree and no invalidation code to get wrong. You pay for that on every write forever, and if your write rate is high while your read rate is not, it is a bad trade. Write-back gives you writes that cost microseconds and a database that absorbs bursts instead of falling over. You pay for that with a durability window you have to size, monitor, and defend out loud, and with a lot more code: dirty tracking, bounded queues, flush metrics, and a shutdown hook that flushes before the process exits. One of those is a latency decision. The other is a data loss decision. So, how do you actually decide? The question is never, is my cache fast? Every cache is fast. The question is, how many milliseconds of confirmed data am I willing to lose? If the answer is 0, a payment, a ledger entry, an order, anything where a customer has been told yes and it needs to still be true tomorrow, then you have already answered it. Write through and pay the milliseconds. If the answer is a few seconds is fine, a counter, a session, a cart, a last seen timestamp, then write back and go and do the unglamorous half. Bound the queue, monitor the flush lag, flush on shutdown. And if nobody on your team can say what that number is, that is the actual finding.
If that changed how you look at a cache, that is exactly the idea. One concept all the way down to the code that runs it. Hit like and subscribe.